actually cut this little exercise. Wait a minute. All right, what's your conceptual question? Is it based on this?
So we're just a little confused about using a mining site to generate local regions that we're interested in, right? So if we run an intersection of 2,000 base pairs upstream of a mining site, and then a mining site, how could they possibly intersect?
Okay, so you have to pay attention here to what you are intersecting. So let's go back to our question. Our question is, which promoters are bound by NFKB? So we have a file of promoters, and these are like these upstream regions of genes. And then my genes go from here. So we have a list of a bunch of upstream regions of genes, right? So these are very long regions. Maybe this will be my promoter. Then we also have a file of binding sites. Binding sites are these very short fragments. NF-kappa B will bind some promoters, but not others. There maybe will be like a little fragment right here of where we've identified an NF-kappa B binding site that falls within the larger promoter region. So in this example, I don't like this example. If our A sample is a promoter region, and then our B sample is a binding site, if I do an A promoter, I guess it's dash A, and dash B binding, and I specify my output as dash WA file dot whatever. What is going to be in this file? And how is that different than if I do dash A promoter dash B binding dash WB? How are these two files different? Go ahead.
One will give like the size in terms of the versions, right? The second one will give it in
Perfect. So this output is going to be a list of promoters that were bound by NF-kappa B. This output is going to be a list of binding sites for NF-kappa B that fell within promoters. So when you specify dash WA or dash WB, you're telling it, I want you to output the regions based on A. Or I want you to output the regions based on B. If you want an output of both, you can specify that. If you want an output of only the things that overlap, you can specify that. So the dash WA in this example, say we had a region like this that's bound by our promoter. If we give it the dash A option or the dash WA option and have promoters as A, this entire region is going to be defined in our output. But if instead we give it the dash WB, only this region is going to be defined in our output. So this is what it comes back to, what you decide to use as a user, and why there's so many different flags here that you can specify a million different things depending on your question. If your question is, which genes are bound by NF-kappa B, what output would I need to ask for? If I want to know the genes that are bound. What? WA, right? Because this is going to give me an output of the genes that were bound. If I want to know where in the promoter NF-kappa B was binding, what output would I want? If I want to know specifically what the binding site of NF-kappa B was, but only for binding sites that fell within promoters. Is what? So if I want the output to be my NF kappa B binding sites, I need to specify to output this binding information. And then the file that you write it to will be the same format as whatever it was. So our format for promoters was GTF, and our format for binding was bed. So when you make a new file that's the result of this intersection, if you do the -WA, you're going to want to give it your extension of GTF, and you should see that the file's format, if you give it -WA, this file is a subset of this master file. This file will look identical to this, but will only contain rows that had binding information that we defined in -B. Vice versa, this will be a subset of the full binding file, but it will only be the binding sites that fell within promoter regions. Okay, so I think you guys did a really good job getting started with bed tools. A lot of you figured out what the commands were. You figured out how to install it, which was great, and start using it, looking at the documentation. You're asking the right questions, and ultimately what you're going to need to do is just try it out. I've only learned these things by doing a million of different intersects in a million different regions. It's really helpful if you very clearly define your question first, and then look at the documentation to figure out how you're going to answer that question. Okay, so I'm going to cut that exercise here. You guys can continue working on it on your own. You have asked for an explanation of how you install things that are not available with Anaconda. So if you guys have any more questions in working through the bed tools exercises, work with each other, so continue to talk to each other. There's also a shared notes document. I noticed we didn't use that a ton, which is fine, but if you're working on this again later and you find something interesting, feel free to share it with your classmates in the shared notes document. And if you really get stuck and can't figure out what's going on, feel free to send me an email and I can try to help clarify if you want a better understanding for how all of these things are working. Okay, so we talked a lot in this class about installing things with Anaconda. I'm going to mention the other way that you install things, and this is going to be this is the other most popular thing that I use. This is GitHub. We referred to it a bit. It's where people, code writers, code developers, will put their code, make it publicly available, and it's done in a way that other people can download it, they can contribute to it, they can make changes to it. In the syllabus, there's a link to a TED Talk by, oh god, I'm failing because I don't remember his name, but he's the guy that invented GitHub and invented Linux. It's kind of a fun TED Talk if you're interested. But the point is that programmers will write this code, and this is where a lot of the programs that we use, like Star, you notice had a GitHub page. Almost all of the programs that we're using have a GitHub page. And if you want more specific details about the code, about documents and anything like that, all of it's stored on GitHub. So main packages that everybody uses are going to be put in BioConda or Anaconda and available for install with Conda. But if you're doing something that maybe somebody else has written but it hasn't like blasted out to the field yet, so where everybody's using it, so it's not put up in BioConda, you can download code directly from GitHub. So this is Olga's GitHub. She's a bioinformatics expert wizard in my lab. I've learned almost everything I've learned from her. And she writes a lot of really great, useful code that I like to go download. So this is her GitHub page, but anytime you see something in a paper that says, you know, we wrote this program to do this, and you want to try it out on your data, they'll give you a link to GitHub where all the code is available. So GitHub has various repositories, depending on what it is. For example, one that I use a lot, it's called KVector. So when you click on a specific repository, this repository is called KVector. You can think of it as its own like program. So it would be like a bed tools or a FastQC or a Star or whatever it may be. So here is KVector. I can't install it with Conda install KVector or Conda install BioConda KVector because it's not uploaded on any of these channels. So anytime you want to download code from GitHub, you'll notice that there's a click over here that says clone or download with a link. And you can go to your home directory. And the way that I have this set up, I have another folder in there called software. So anytime I download something that's not in Anaconda, I put it in my software folder. So I can go into software and I can do git clone. And it's already there, so it's not going to let me do it again. But when you do this, it's going to create a folder for that particular download that we've made. And this folder is going to match what's on the GitHub page. So anytime you're downloading something where you have to figure it out on your own, there's always a README file which will give you more instructions on how you download. And you'll see in here, here's the installation. So it's git clone with the link that you've cloned. You can go into that directory and you get the instructions right here. Install it with pip install. And it tells you to add a dot there because that means install this in the current directory where I'm at. So once I run this install, it will go through, and this is a Python package that I can import in my notebook. And I know that because I see examples in the documentation where they're providing different things in the different commands that are available in this package. So if something's not available to you on Anaconda, GitHub is a great place where a lot of the code is stored, and you can get it with git clone. Git in itself is another very useful package and has a lot of other features that I chose not to teach in this class because it can be a little bit confusing. But if you get really hardcore into the computational stuff, you'll be using Git a lot more. Yeah?
So I tried git clone and permission denied.
Don't use the one in here. Did you copy it from here?
Yeah.
Copy it from that link. Because I think the one that she has in the example is like her specific one.
So did you put the command back on?
So clone or download, you copy this link, and then it's git clone. And then you paste your link. And then it will make a directory, and there will be a README file in there that you can use. Yeah? No. But you should watch the TED Talk because it talks about how they deal with this. It's the idea that whatever the master code is should be working, and in most cases it is, but GitHub is built in a way that you can make a branch of the master code when you make changes to it, and then as soon as you're happy with your changes, then you push it back to the master branch and update those changes. So for the most part, yes, all of your code is going to be up there and working, but people follow these rules to varying degrees of usefulness. So yeah, GitHub is a great resource, and if you guys want to know more about it, there's a lot more that you can learn. But for now, this is the basic way to install it. And watch the TED Talk if you're curious. It's interesting. Okay, so if you have any more questions, feel free to let me know. Again, you guys will have access to all the information that we've done in this class. I'll also be around for a very long time. I'm only a second year. So if you guys are running into any of these computational problems or things that you're trying to work on, feel free to shoot me an email. I'd be happy to try to help point you in the right direction. I was sitting where all of you are a year ago, and it was the most frustrating thing in the world. But fortunately, I had people around me that were experts and that I could always go to and ask for help. So I realized how important that is. And if you guys don't have that, feel free to send me an email, and I'm happy to help. Before we break for lunch, I'm going to send you guys a link to a class survey. Please take the time to fill this out before you go to lunch, which is in the conference room next door. Again, we really appreciate your feedback for all of this. This is the first